Hello everybody. Today in this session we continue the basics of transformer where we left off in the last session. In the last session we had been discussing about the transformer and its phasor diagram and how it is represented as phasors in the spatial coordinates. We also represented the symbolic form of the transformer, and today we will continue the discussion from that point onwards. So, we have this transformer with a primary, a core and the secondary. One should not forget to put the dot polarities. This is to indicate that this part of the winding is in phase with this part of the winding. And there is one more information that we have to provide, that is N1 is to N2, that is the N1 number of turns or N2 number of turns. Alternatively, one may also provide the ratio, that is 1 is to N, where N is equal to N2 by N1. This is also a frequent representation of the transformer. Instead of the actual number of turns, they provide the turns ratio. N is called the turns ratio. This is called the turns ratio. Secondary turns, number of turns to the primary number of turns. And of course, we have the primary voltage E1 with the primary current I1, secondary current I2, secondary voltage E2 with some load connected at the secondary, some Z2, and there is a source here which is connected across the primary, which is the generator. It's an AC generator and we call that EG. So, we saw that the phasor diagram in the spatial coordinates, that is the alpha beta coordinates, the beta alpha, we have EG and E1 are in phase because they are one and the same voltage. Now, the dot point of E1 and the dot point of E2 will also be in phase, and therefore, let us say we have E2, and then I2 is going to lag E2 by lag or lead E2 depending upon the impedance. If it is RC or it is a lead network, then I2 will lead E2. If it is a lag kind of a network, that is inductive kind of an impedance, then I2 will lag E2. Let us say it is a lagging impedance, then you will have I2 just like that. Then I1 and I2 will be in phase, only the difference is by the turns ratio, and this is going to be I1. So, E2 is equal to N E1, I1 is equal to I2 by N. So, this is the phasor diagram. Then we also noted that inside the core there is a flux linking phi m, and from the Faraday's law we see that the induced EMF is equal to N d phi by dt, which is equal to N j phi m. Now, induced EMF E is in this direction, this is E1 direction. that is if you are taking the induced EMF across the primary E1, N1, N1, phi m. So, either E1 or E2 one could take, and we know that they are in phase and they are along the alpha axis. Now, phi m lags E1 by 90 degrees because of the J operator. What it basically means that if I have phi m, now the vector of phi m direction is rotated by J, which is rotated anti-clockwise plus J, rotated anti-clockwise by 90 degrees to obtain the direction of the induced EMF or the induced voltage, which is E. So, this would be the phi m direction. So, this is the phasor diagram for this idealized transformer. Now, let us have a simple example to understand the various points here. So, we have a source, an AC source, so the AC source is connected to the transformer terminals. There is a core and it is a step up transformer, let us say, and this is connected to a load as shown like this. So, this is our EG, generator voltage. This is E1, the primary induced voltage across the primary of the coil. There is an E2, the secondary induced voltage across the secondary of the coil. This is Z2, the secondary impedance that is applied across the secondary terminals. We have N1 number of turns here, N2 number of turns here. There is a primary current I1 flowing into the dot. There is a secondary current I2 flowing out of the dot. And of course, there will be a flux which links the two coils and causes the energy to flow from the primary to the secondary. So, for this circuit, let us say we have 200 volts 50 hertz as the source, and let us say this is 90 turns and this is 2250 turns N2. Let us say that there is a load current of 2 amps that is flowing with a lag angle theta of cos inverse of 0.8, or power factor equals 0.8. Let us say lagging load, which means Z is inductive RL kind of a load. Now, this being the description of the circuit, let us try to see what informations that we can extract. And this is a 1:n transformer. Okay. So, let us first see what is the turns ratio. So, the turns ratio is n, which is equal to n2 by n1, which is equal to 2250 by 90, which is equal to 25. Then let us see what is the primary current. I1 equals what? The secondary current is 2 amps, because RMS. All the values generally are that are mentioned are effective values or RMS values unless otherwise specified. So we know that N1 I1 ampere-turns should be equal to N2 I2 ampere-turns. And also from the power equation, we also have earlier seen that, let me use the same notations. N1 I1 is equal to N2 I2, because we see that I1 by I2 is equal to N2 by N1, this inverse proportionality for the currents. So therefore, we have I1 which is equal to N into I2, which is 25 into 2 amps is 50 amps. So for a 2 amp secondary current, the primary current is 50 amp RMS, because it is a step up, because it is a step up transformer. Now let me select this portion, copy it, go to the next page, paste. Third point, E1 equals 200 volts. So what is E2? E2 is equal to N2 by N1 into E1, or in other words N times E1, which is equal to 25 into 200, which is 5000 volts. Note, E1 I1 is equal to 200 volts into 50 amps, which is equal to 10,000 volt amps. E2 I2, which is equal to 5000 volts into 2 amps, which is equal to 10,000 volt amps VA. So this power balance should happen. Then what other information can we extract from this, from this particular diagram? What is phi max that one can extract from this diagram? So, we know that E is equal to 4.44 N AC BM into F. What is this one? Flux density into AC is nothing but phi max or phi m. So, E is equal to 4.44 into N into F into phi max or phi m. One could take either the secondary side or the primary side. Taking the primary side, we have E equals, E is 200, 4.44, N is 90 turns on the primary side, 90 turns on the primary side. Frequency is given 50 hertz of the, and then phi max. This is the only unknown, and therefore phi max can be calculated, which gives about 0.01 Weber or 10 milliwebers. So, like this we get the information about the transformer using basically the fundamental law which is the Faraday's law of electromagnetism, and also one more law which is the Ampere's law. Now, let us draw the phasor diagram for this circuit. So, to draw the phasor diagram, we take the two axes in the spatial coordinates. This is the beta axis and this is the alpha axis. So, the alpha axis direction is taken as EG direction, the generator voltage direction itself. So, we have E1 which is 200 volts and we have E2 which is 5000 volts. E1 equals EG, of course, and what is given is a lagging load. I2 is lagging E2 . This is I2, this is lagging E2 by an angle which is cos inverse of 0.8. So, cos inverse of 0.8 is 36.9 degrees. So, therefore, this angle is 36.9 degrees. And what about I1? I1, now this I2 is 2 amps, I1 is 50 amps, of course I am not, this is I1 which is equal to 50 amps, and then there is phi m, this is phi m which is 10 milliwebers. Phi m is also in RMS quantity because it was calculated using RMS quantities. So, this would be the phasor diagram for this transformer circuit. Is that clear? Okay, now